Hello people. As you can see, I'm working on the milling machine and I was trying to prepare a test piece for the new Coromill 745. And I almost got it finished, and I was using this nice Sandvik Coromant R300 face mill with round inserts. And it was working great until something happened and the machine does not start again. I run into some kind of an electrical problem. I was supposed to show you testing out the new Coromill 745, but it turns out that this video only contains the trying out of this Sandvik Coromant tool and also testing out my milling machine until it broke down. So let me get the problem fixed, and in the next video I will show you the new face mill. But in this video you're gonna see as far as I got preparing this piece. I got some pretty nice cuts done. I think you will like it. And I also have some explanations about cutting. So the things that I explain on this video are how I feel about things. They are not truths. You should decide yourself how to use this information that I'm giving you. I don't want to teach you. I don't want to teach anybody. I'm no one to teach anybody. I'm just an amateur machinist. So I hope you enjoy this video and the nice cuts, and hopefully I will give you some ideas with the stuff that I'm telling you. But don't take anything too seriously. Okay, getting ready with the test setup, and in my voice I have a pretty large piece of mystery steel. I think it's some kind of a mild steel, but no real info on what it is. And first I'm gonna use this Sandvik Coromant as well, R300 round insert tool, to rough out the size of this piece. So I'm gonna rough out here a little bit and then flip it 180 and do the same thing. And then I'm gonna set this piece on its back on the vise with some parallels, so that I can cut on this side or the other side with the new Coromill 745. And I don't want to use it yet because this is, the sides are not true and not parallel, and this setup is not the most rigid. So I want to use this tool and these used inserts to do this, so we can use the new mill with some better conditions. So and by the way, this is also a great tool. I love this, and this is one of the tools that I got with the 745. So let's lock the quill first and let's get a touch. Okay, we have a touch. And I'm gonna climb mill this, just putting a little bit of tension on the gib on the x-axis. And the Sandvik book says that it's not good to have the tool set so that the insert touches the edge of the workpiece at a 90-degree angle. So I'm now a little bit over the center of the tool. I guess that's because it produces less shock to the inserts. So let's let's feed in 1 millimeter to start with. And first let's use a feed of 200 millimeters per minute, and then hopefully being able to ramp it up a little bit. Let me get you some better lighting. Can you see now? So let's try another millimeter and double the feed. Okay, doing quite well. Let's try 1.5 millimeters. So why I'm doing this is to finally actually test this milling machine and also test some of these tools. And of course for entertainment for myself and hopefully for you also. Okay, really good finish. So I guess this proves that even on manual machines you shouldn't be too afraid of using higher feeds. Especially on this cutter, because it has round inserts. When you use shallow cuts, the lead angle on the insert is very, very shallow. So you produce a long chip, but it's very thin. So you can compensate that for by increasing the feed rate, which is also called high feed milling, I think. So that's what I'm trying to do a little bit now. So I guess we're doing pretty fine. What should we change? I think the feed is pretty good. The spindle speed now is it's only 560. So I think we can increase that to 800. And hopefully not getting chatter yet. But what's gonna happen first? What's gonna be the first issue? I think will be chatter. Okay, let's see. And this is a little bit noisier here. This is 1 millimeter. Okay, still doing very well. Now that the spindle speed is increased, the feed per tooth also decreases. So let me try to up the feed a little bit. So it's now 400, let's go for 500. I guess that's enough. So let's try how it goes and then maybe push it a little bit further even. Okay, that was very nice, no issues. So, what I should try next, I think, is to increase the depth of cut. Sorry for my pronunciation. So, last time it was 1 millimeter, so let's try 1.5 now. Okay, now it's 1.5. Let's see. I guess these cuts are trying to require some horsepower from the motor, but I still haven't heard it slowing down at all. But it's only a 4 kilowatt motor, 4 or 3, I think it's 4, so there's not a whole lot of power available. Let's continue. Okay, the shaking from the last cut was actually made because the entering angle of the insert was exactly 90 degrees. So that really seems to make a difference, even though it was cutting only a slight amount compared to this side. It was making a lot more nastier sound. So I wonder if what I should try next. I think I really would like to find the limit and hopefully still staying safe. But I think I'm gonna keep going like this on this side, and maybe on the other side I will try some more. But this setup actually seems to be pretty stable. I tried sticking my finger in here and it's not vibrating at all. Let me check the tightness of the vice to the table, I mean. And if you watch this and listen to me, you should know I don't want to teach you anything. I'm no one to teach anyone anything. I'm just an amateur machinist. So what I'm talking about is what I think about things and how I have learned. It's not the way to do things. So use your own head and criticize what you hear me say and make up your own mind. I just want to give you inspiration and ideas and something fun to watch. And from that topic to another. This is one of the chips. It's still pretty thin. I think I could try some more feed rate. So let's bump it up a little bit. Let's keep this spindle speed. I know the cutting speed is not, I think it's about 150 meters per minute at the moment. But I don't have the box for these inserts, so I don't know what kind of speeds they are rated for. So I like to stay on the safe side. Okay, so let's try another 1.5 millimeters and up the feed to 630 millimeters per revolution, which should be, let me think, it should be, I think it's about 0.2 millimeters per tooth, which is starting to be a pretty thick chip, but as I said, and the lead angle on these round inserts is so shallow that the chip will not be thick. Okay, the feed is now up, and first let's try 1 millimeter and then go 1.5. Okay, that's starting to be a fast feed, and you can see it's also leaving a pretty rough texture on the piece. It's still shiny, but it's rough. I think maybe one of these inserts is, maybe they're getting worn, or maybe it's just the high feed rate. I think it's just actually the high feed rate, and also it might be the wear on the inserts. Or having the inserts misplaced somehow. One cutting deeper than the others. These shouldn't be too worn inserts yet. Okay, let's try 1.5 now. Okay, it's still doing great. I'm not sure if I mentioned you already, but of course what's happening when the depth of cut is increasing with a round insert, you're getting less lead angle all the time. So the deeper you go, the thicker the chip will get. And also the harder it will be for the inserts and for everything else too. So I think this is a pretty good setting. I will keep going with this. Or should I increase the... No, this time I will not increase anything. I have now taken off 9.5 millimeters, so I think maybe I should go a few millimeters more and then flip the piece. I just want to make it so thin that it will fit between the jaws of the vise. Let me show you a little bit larger view, having the light sitting on the camera. I think that's enough. And I can see that the camera is vibrating, especially on the narrower cut right here. But I hope you still get a pretty good view. But it's not making any chatter. It's just some kind of vibration, but it's no chatter. There's always some kind of trembling going on in a milling machine when it's doing the interrupted cutting. Milling is always interrupted cutting, so the inserts are all the time entering and exiting the workpiece, which always produces some amount of vibration. But I think harmonics is what we try to avoid. And of course, vibration is always bad, but some amount of vibration I think you always have. The less the better, but you always have some. Okay, I think we're now ready to flip the workpiece. And I think let's also do the other side using this tool and save the new tool for the cleaner cuts on these ends. I think I can still show you the other side. And by the way, here's a shot of the chips that I produced in the previous cuts. Not sure which chip is from which cut, but I think this is using the slower feedback tooth, and this one looks like it's a little bit thicker. And I think this is the kind of chip thickness that you would like. And you can see it's, of course, the thickness starts from 0 on this end, and then it increases until this side. Okay, ready for the other side. And one more thing I want to say is that I hate conventional milling, even on a conventional machine. Once you adjust the gibs and maybe even set a little bit of pre-tension on the gibs, which I think will cause premature wear. But if you keep the ways well oiled, you can do that, at least to some extent. But when talking about tool life, climb milling is way better than conventional milling. And also on surface finish, climb milling is way better. You can experiment on that yourself, and also there are quite a few nice videos about that on YouTube. And I think even on conventional milling machines, it's a good idea to try to do climb milling, and try to avoid conventional milling. And now that I'm talking, let me say you another interesting thing that I learned from the Sandvik books. In most milling operations, Sandvik Coromant does not suggest you to use coolant. So general milling operations, especially on steels and cast irons, you should try to do dry without any coolant, because the coolant will cause temperature shocks to the inserts. And even though the insert will get hot without coolant, and they are designed to withstand the heat, but actually if you use coolant, every time the insert exits the cut and it's hot, it's cooled down instantly by the coolant, and that causes thermal cracking. So I think it's a common belief that it is a good idea to use coolant when milling, but I was actually also amazed to find out that in most cases that's not true. At least that's what the Sandvik book says. And I think that's maybe the most resilient source for information that you can have. And putting it that way that the book says, I think it makes perfect sense. So that's one more thing that I have recently learned. Of course, it's different when using high-speed steel tools because they have much lower red hardness. So in other words, they don't like heat as much as carbide tools. And also when milling aluminum, it may keep the chips from welding to the cutting edges. And when working with cast iron, it helps with the dust. And actually, if I remember correctly, I should check this, but I think on aluminum it was actually recommended to use coolant. And there were also some other metals that they really recommend to use coolant with. But on steel, no. Okay, let's keep on cutting. I wonder if I should change tools. Maybe not. Let's go with this one. I have another tool which I kind of would like to show you, which is this one, also from Sandvik Coromant. It's an R390 using these inserts. This is a 25mm or a 1-inch tool with just 2 inserts. I've used this quite a bit and I love it. It's also great. Yeah. And the situation with this type of insert is of course completely different than the round inserts. And also, now that I'm still talking, let's talk a little bit more. The cutting forces on a round insert are way different than on a square insert. And actually, not just square insert tools, but pretty much all high-feed tools. Most of the cutting is done with a shallow lead angle, as I said before, which causes the cutting forces to go up into the spindle. So there will be more axial forces than radial forces. And with this type of tools, pretty much all the forces will be radial. And in most cases, when you try to avoid chatter, it's better to have more axial loads than radial loads. Especially when you're working, I think I would say this is a pretty good example of where axial forces are better than radial forces, especially if this was a little bit more thin piece. Because if you have radial forces, you will try to push the workpiece sideways, but now you will just try to push it down. And of course this piece is much more rigid in the axial, the up and down side than sideways. Of course that depends on whatever you're doing and what kind of a machine you have. Some machines may have the spindle bearings designed to take more radial loads than axial loads, and some vice versa. And actually I think, not quite sure which this machine would like better, but I think, actually I don't know, but the Sandvik book says it's better to have axial loads than radial loads. I think somehow axial loads are easier to take on any machine than radial loads. And you can also see that because the spindle bearing is around here, the radial bearing, actually it's even a few centimeters or maybe about 1 inch upper than my finger at the moment. So there's about 15 centimeters or or 6 inches from the spindle bearing to the cutting, to the place where the cutting takes place. And this will try to, of course, bend the spindle, and it has some leverage which will increase the actual radial loads on the radial front spindle bearing. So if you had a short tool which is close to the spindle bearing, I think it might be better to have radial loads. But now that you have a long tool, I think it's actually much better to have axial loads, because the length of the tool does not give any leverage on the axial load direction. Okay, that's just my thinking. And this is a good tool because I'm using this with a collet. Of course, you could also use this with the what it's called. Can't remember what it's called. It's a weldon shank, of course. Weldon holder, of course. So you just slide it in and tighten these screws, and that's a very, very good method. But I don't have any of those holders. I should get some. So what I was saying is that you can have a very short stick out with this tool, and that's why this is also a pretty good tool, I think. A rigid tool for some good cuts. And of course, also with this tool you can have lots of cut depth, because the lead angle stays the same even though you go shallow or deep. And of course you should try to take deep cuts with these, with little side step, because you want to use this whole cutting edge and not just the tip of it. So it's better to take deeper cuts and going sideways less than taking shallower cuts and going the full width of the tool. That's how I would do. Not necessarily the right way to do it. Okay, let's keep going, finally. Okay, this is a 2mm cut. It's the deepest cut I've had so far. Let's see how it goes. Another one. I think I broke something. Some kind of an electrical failure. Oh, not too good. Well, actually I was just about to say that the machine is cutting very well. And I am satisfied and also surprised how well this is actually cutting. But now it broke down. Nothing happening. Trying to switch on. Okay. Let's try to find out where the problem is, but I think you will have to wait until the next time to see the new Coromill 745 cutting. So until the next time, let's hope I get this machine running again.